Hello, everyone. My name is Shalyn McCoy, and on behalf of the Atlantic Salmon Conservation Foundation, I'd like to welcome today's webinar. The series is made possible in part in thanks to the contribution of Government of Canada. And for today's webinar, we're really pleased to be hosting Dr. Antóin O'Sullivan. Antóin is a postdoctoral fellow in forestry and environmental management at the University of New Brunswick. His main research focus has been on linking landscape structure and composition to the spatial temporal variability of river thermal and flow regimes, forest hydrology, and remote sensing. And Antóin is co-pi of UNB's Interactions in Tomorrow's Environmental Laboratory, where he leads the Airborne Remote Sensing Unit. He also leads projects on ecohydraulics, ecology, ecophysiology of salmonids, and precision farming, as well as collaborating on groundwater projects. To date, Antóin has published 19 papers with several more in review. He's also a Gemini. His favorite color is yellow, and the word for his favorite is Wellington. Today, he's going to be speaking on waterscape continuum, rethinking boundaries in ecosystems. After the presentation, we will give the opportunity for those that are participating today to do some questions and answers. We'll let you know how to do that when the time comes. But for right now, I'd like to turn the webinar over to Monsieur Antóin O'Sullivan. Welcome, Antóin.
Thanks very much, Charlene. All right, I'm going to share this screen here, and you can just let me know whether you can see it or not, and then we can go from there. So you can see this this opening slide here.
It looks perfect.
Okay, awesome. Thanks very much. Well, first I'd just like to thank the ASCF for their continued support for the research that our group does. Really, since starting my PhD, it's been always supportive of research. So thanks very much for that. And then thanks for the opportunity to present here today. And I hope I don't bore the backside off people. So this is work that kind of has been in my mind since I started my PhD. When I first started my PhD, I didn't really know what a watershed was or a catchment. I'm an engineer by training, and I studied geomechanical engineering. So when we talk about watersheds and what have you, I was always thinking about things that are going on in the ground. So this is kind of it's nothing new really. I'm stealing work from other hydrologists, but trying to apply it to ecosystems. So that's where this idea of the waterscape continuum came from. So hopefully I can shed some light on that, and hopefully it gets people's gears thinking, or gears clicking in their head. And this, of course, is the co-author. This is my postdoctoral supervisor, the man, the legend, Tommy Nassari. So this is work from both of us. All right. So just by way of overview, then, first I'm going to go through the hydrological cycle, and I'm going to look at it, kind of bring you guys through it in a bit of deep time, so perhaps a way that you haven't looked at it before. And then I'm going to speak about this waterscape idea. It's relatively simple, but hopefully I have some illustrations that may get you guys thinking maybe in terms of 4 dimensions rather than topographical dimensions or 2 dimensions that we typically think of. And then because this is an Atlantic Salmon Conservation Foundation, I'm going to give examples of a waterscape settings and how they relate to thermal refuges of salmonids. And then finally a summary, so I'll just wrap it up. All right, so I'm hoping people can see my cursor here. So this is the hydrological cycle. I know everybody knows what this is, but let's just bear with me so we're all on the same playing field. So of course, you may start with water in the atmosphere, transcends to ice or snow, precipitation, so snow, or rain. And then you may have snow melt or runoff to the streams. Some may infiltrate into the ground. Some will go over the ground. You end up with springs or groundwater tributaries or surface-dominated tributaries, so no groundwater connection. And then you have freshwater storage systems, so lakes, wetlands, rivers, streams, what have you. All of this will flow through to the ocean. You've evaporation, and then the whole process is going to start again, and transpiration through trees. So this is essentially the water cycle. We all know this from school, I'm sure. However, is this all of it, or is there more to it than what we see within this panel here? So there's also a role of water way deep in the Earth system. So this is a really neat paper that came out in 2014 by folks from I think it's the University of Alberta. And what they found was this mineral, ringwoodite, and within that mineral, it was about 410 to 640 kilometers into the Earth's mantle. They found water in it, which is just quite incredible because the temperature gradients there are so enormous. However, with those temperature gradients comes very high pressure gradients, changing the boiling point of water, so it doesn't burn off. And we have this massive water supply way beneath the Earth's surface. And just for context here, this is an illustration where you have a primary and atmospheric water cycle. So what we're typically thinking about is this atmospheric cycle driven by solar energy. This panel here, or this ellipse here. However, if we think about Earth through deep time, we have a much deeper primary water source. Estimates are about 2 billion years old to this 2 to 3 billion years old. Of course, our estimates, they're probably wrong, but it just gives us an idea of how deep in time this goes back. There was some models built for this as well. So this transitional zone here, there's an estimated between 0.5 and 12 times the amount of water in this area here as there is in the Earth's oceans. So it's just quite mind-blowing to think about. And of course, it's this water then changes the chemistry and the thermodynamics within the mantle, and this will ultimately influence Earth's continental crust. And of course, then everything will cascade from that. So really, water is not just important for surface processes, it's important for Earth processes in general. It's just quite incredible. And of course, then we have surface processes of water. So we have exogenic, meaning on the surface. Ice, of course, a massive geomorphic agent, especially in Canada, we see here a post-glacial landscape. Of course, water, we're all familiar with that, erosions, banks falling in, what have you. And then there's solutions. So this is chemical reactions where water is the medium. We have this karst landscape here where you see these interesting features. So all of these things are connected, of course, by water. And there's also a role of water in the Earth's biosphere. And the reason, so just for context, the reason I'm doing this is just to show you how all-encompassing water is. So if we think about water is the matrix of life, really eloquently stated. Water is the matrix of life, of course, and you can see this from different scales. So if you look at the structure of a cell, 80% of the water, 80% of a cell is water in the cytoplasm. Again, the presence of water is omniscient. And this is also really interesting towards the evolution of our own species, or hominins. So this is a really neat paper by Mark Cuthbert and Gail Ashley from 2014 in PLOS. So what they were interested in is looking at this phase of our evolution. And what they did was they linked this phase of our evolution to a drought period. There was a massive drought period in the East African Rift System. And how the hominins actually survived was they were utilizing these groundwater discharge areas. So there were springs and wetlands here. And just for context here, we may have a groundwater discharge wetland here where we have subsurface flow into the wetland, this groundwater. And the reason for that it's persistent and that it can be a drought refugia for plants, for fish, and for, of course, hominins, is that those water refuges operate at different time lags than, say, a climatic shift may, or even interseasonal or interannual or interdecadal or maybe even intermillennial. They may be massive time scales here, but it's this groundwater that basically kept hominins tipping away so we could then ultimately spread out through the earth as we are today. Just to bring all this back together then, my point here, which everyone knows I'm sure, but I was just trying to give a big picture of it, is that water is essential for all processes and life on Earth. Okay, so in ecology, I'm going to change gears here. There are different concepts where we try to explain patterns in ecosystems. There's concepts of continuity and there's concepts of discontinuity. So this is the most famous one, unquestionably, is from Van Oud et al. in 1980. And this is the river continuum concept. So basically, you have differences in processes that follow the stream order across a catchment or a region. However, others have suggested that we have serial discontinuity. So you have punctures where you have shifts from one part to another moving through the river system. And then we have, of course, it's not just limited to ecology in aquatic ecosystems. There's landscape continuums for terrestrial ecosystems. And even in geomorphology, this is a really awesome paper by Gordon Grant et al. From 2017, where they were talking the fact that you can have both a discontinuity and a continuity together. And of course, it's not just limited to that. Then we have hypereal exchange, conceptual frameworks, and then a really nice paper by Ward, old school, 1989, I'm looking at the 4 dimensions of lotic systems, so river systems. All of these things, again, they're trying to explain the patterns that we see in ecosystems. However, if we take a segue for a moment and think about the world through the lens of a hydrologist or a hydrogeologist, we can really lean into the work of Tom Winter. Tom Winter is one of my heroes. If anybody has time, this is 1998. Kind of, I guess his thesis really is what you call it. He was looking at groundwater and surface water as a single resource. Probably it's the first book I read when I did my PhD, and it's just an incredible book. And from that, you can start to see how, well, water actually, the persistence of water differs based on what he would call hydrological landscapes. And those hydrological landscapes then are a function of your topography and your geology and your climate. And then, of course, you can take that a step further, and this is by Josef Toth, Hungarian hydrogeologist, who's actually out in the University of Alberta, just an absolute mega mind. And Toth here starts to bring in the idea that groundwater is a geologic agent, but of course it's also an ecosystem agent too. And you can see just the things that this man was thinking about: redox, different flow potentials. Of course, you can put, so you've freshwater springs here. You can put whatever vegetation would co-occur with that. So really, they're starting to flesh out this idea that we have to start looking at the subsurface to explain not just what's going on the surface in terms of hydrology, but then in terms of ecology too. And that kind of brings us to this Gail Ashley. So one of the co-authors on that 2014 hominin paper, this lady was probably one of the first people to coin this critical zone term, and that's becoming more and more popular. So the critical zone is essentially going to treat the entirety of the subsurface to the leaves of the trees as a continuum or a continuity, and that is the area where most of the life occurs on Earth. So again, nothing novel here in what I'm about to present, but it kind of tethers all this thing together, I hope. So this is a paper we published earlier this year, and this is the reason for this talk is this idea of a waterscape continuum. And really, what it's trying to do is to show ecologists, or to highlight to them even, I'm sure they know, the importance of this interconnectedness from the surface down through that critical zone, and how this is impactful for ecosystem functioning. So if we think about this panel here, and if we start at the very bottom here, let's say we have a landscape. So if we have a landscape, and this area here is CZ, that's the critical zone. Okay, so the critical zone occurs across the landscape. If then in this landscape you may have a catchment, and within the catchment you have a riverscape. Okay, and these are terms that we know pretty well. My suggestion would be that the thing that binds all of these things together is going to be water. And so if we think about it in terms of this panel here, it looks like a lot, but we'll go through it together. So this waterscape continuum is going to be inclusive of the surface water, so maybe a wetland or a lake, and a stream. We have soil moisture that's included in that. Trees will use that. We have rock moisture. Trees will also use that. And then we have the groundwater component. So what I would suggest in my feeble brain is that what the continuum that exists across the landscape is water. It's continuous, and it doesn't have the boundary of topography because it's going through geologic materials. And here you can see, so we have hydraulic conductivity here, this gray gradient here. Low hydraulic conductivity is essentially water does not move through that material very easily. And for simplicity's sake, we can just think about it in terms of that low hydraulic conductance material doesn't store a lot of water. Further, it takes a very, very long time for the bit of water that's in there to move through it. Okay, so you can see here the age of the water on the graph. Very dark is old, so it would be this arrow here, a very weak flow path, so not very much water coming from it. But as we go into this area here where we have fractures and maybe hydraulically conductive rock like a sandstone, in an area where we have rainfall to recharge it, we can see that it's going to have a much stronger flow path and it's going to percolate into the system. We also have recharge points here where we have an upland wetland is going to recharge into that soil and that bedrock, and we have these discharges. So my viewpoint is that we have to treat these entirely as a single unit. But the thing is that the expansion or contraction of those units, so how essentially a wetland would contract, how the groundwater table will contract, how the soil moisture contracts, how the rock moisture contracts through space and time is going to be driven by the hydraulic conductivity, of course, the use of water by vegetation or biota, and then the geologic material itself, plus the energy gradient. So that's a lot to take in at the moment, but hopefully it becomes more apparent in these couple of illustrations we have. So just to recap, the waterscape is all of this water. So it's the river, it's the stream, it's the wetland, it's the lake, it's the soil moisture, it's the rock moisture, and it's the groundwater. And it's how these things expand through space and time is going to have an influence or a primary role in how ecosystems operate. Okay, so let's think about this in terms of river temperatures then. So this is what I did my PhD in, so this is kind of my happy space, and hopefully I can explain this pretty clearly. So on the top panels here, so A, C, and E, we have, let's say we have wet conditions. And in every single panel here, these 6 panels, the topography is identical. So there's no difference in topography. What differs, however, is the underlying geology. So we have areas, so low hydraulic conductivity to high hydraulic conductivity. This area is not going to hold very much water, it's a bit darker, but this area may hold more water. It's maybe in that Goldilocks zone where it holds a lot of water and releases it back out to the system nice and slowly at a stable rate. In this instance here, it's not going to, there's going to be some discharge of water there, but it's not very deep, so it's going to be relatively responsive perhaps to climate or changes at interseasonal and interannual timescales. But this unit under here does not hold very much water. So if we look at that, then we've got to think about how does this affect the stream thermal regimes. So let's think about this wet condition first. Here we have this ellipse. Here is a topographical catchment. I'm going to populate it with a stream. There's going to be some wetlands on it, and we're going to have groundwater flow paths here. The solid arrows are going to be a strong flow line, excuse me, and the dashed arrows are going to be a weak flow line, so not very much groundwater coming from it. Okay, bear with me here because this is quite a bit. So here you can see the color corresponds to the temperature. So the deeper we go down, the cooler temperature we have. And we're in this unit here in panel A where we have a lot of water can move through. But we can see there's going to be a recharge point here, and it's going to discharge here. Okay, so we have a different groundwater system in this area, even though the topography is identical, than we do in this area, where we have barely any groundwater in this system here. We have some groundwater flow paths in here, and in this system, we only have really, really shallow groundwater flow paths. So if we think about it in terms of responsiveness to climate variability, this area here, very shallow, is going to respond quicker to climate change than this very deep area here. And then we can look at the thermal profiles of the rivers. So we're starting the headwaters here and moving downstream. So here we have a wetland in the headwaters, it's warm. Okay, so we have a warm upland wetland. As we transition downstream here, this wetland is going to recharge in here. And then we have this discharge zone further downstream where we have a wetland and the stream, and we actually have colder temperatures at the very bottom of the catchment in contrast to the top. All right. So then let's think about this one. So again, the exact same stream morphology, exact same distribution of wetlands, but we have changed the geology here, and we changed then the thermal regime of the river. So we have a warm upland wetland here, and this wetland is recharging this unit here. We have a bit of groundwater discharging here into the brook. It drops the temperature down, but then we get onto this area that has no groundwater. So this wetland is going to be really influenced by solar radiation loading and air temperature, and it starts to increase then as we move downstream. And finally, if we look at this section here, we have a wetland, a bit of cooling from this really shallow groundwater input here. Then we start to have this warming as we move our way downstream. So the thing here to take home is that the topography is exactly the same. The geomorphology in terms of the sinuosity is the exact same. The position of wetlands is the exact same, but we have different thermal profiles. If we go to a dry condition then, so this is when the waterscape would have contracted, we have none of these flow lines here because the wetland it has changed. And when we look at it, we have a contraction of the stream, so it dries up, the stream contracts. We still have this discharge here into this wetland, but because it's dry, you have the groundwater coming in and it's been influenced by the solar radiation loading, so you have this kind of a it's not cold, but it's not warm. It's like median temperature maybe. And then as we move downstream, we start to see that it gets really cold again. And what happens in this system is kind of the inverse of what you think would happen. During the really low flow conditions, so when that waterscape contracts, we have greater dominance by groundwater. And this leads to stream temperatures that are colder during the dry period than they are in the wet period, because they're now just all pure groundwater. So that's really kind of the opposite to what we would think about, but this is what happens in these systems. However, if you look at this system here, we have further contraction of the stream, but we have an increase in the stream temperature, as you would predict with downstream distance during the dry period. And that's because of the underlying geology here. And similarly in this system then, because we've absolutely no groundwater influence, where we've got a bit of a buffer here, the stream temperature really starts to bake. So here we have, again, different responses between wet and dry conditions. That's, even though the topography is identical, we have differences in the waterscape contraction expansion through time. So just to go over that again, so we have the same topography, we have different geology, different climates or different wetness or dryness conditions. We have different thermal regimes driven by those different geologic gradients, and we have differentiations in how that waterscape contracts and expands through time. And one thing that's interesting here is that wetlands can flip from warm to cold in dry conditions, and this is reported in another paper. So there's a really good review of wetlands by Ulyss, of course, Winter, Rosenberry, DeVito, and there's a bunch of other folks that are doing this stuff too. Okay, so just a quick recap then. I hope this is clear now that topography alone can't explain hydrological processes. In some instances it will do it really well, but in other instances you have to go further than the topography to explain hydrological processes. And this of course is going to have resonant effects for ecosystems, because we've already stated that water is the lifeblood. Excuse me, water is the blood of life. And then the suggestion of course becomes that we need to start to account for this geologic variability, the climatic variability, topographic variability, and I'm going to put in there ecological variability to explain how ecosystems are operating in general. So it becomes a really holistic way of looking at the system, using this idea that the water can expand and contract through the landscape or the critical zone. Okay, so that's about as far as I'm going to go with the waterscape explaining it. Now I'm going to try and show you how these things are actually tethered to salmonids. All right, so this is a paper that my honors student has in revision, and it's the title of his paper is Cooler, Bigger, Warmer, Smaller, Spatially Explicit Species and Size Stratification in Behavioral Thermoregulating Salmonids. Bit of a mouthful, pretty neat paper though. So I'm going to speak about behavioral thermoregulation here for a bit, and hopefully I can decant with a couple of videos what it's about. So what is it? Essentially, salmonids are cold water species. So when they get stressed out, they seek out cold water refuges. This is the behavior that you will see. They'll gather around a cold water source in numbers that you typically don't see. They're very territorial species. This is not normal behavior. However, at the exact same spot, when the temperatures drop back, there's an absence of fish here. So this is the kind of behaviors that you could expect to see, excuse me, with behavioral thermoregulation. So just to give people here an understanding of what we're talking about with timing of the onset for aggregations, let's say we have this temperature of the brook here, and it's moving through the day, so it's cool, and then it moves up to high. So conceptually, the first fish that would appear would be brook trout, lower thermal tolerance than salmon par, and adult salmon, again, lower thermal tolerance. Then we'd have the 2+ par would appear at a warmer temperature, 1+ par appear at a warmer temperature again, and then young of the year appear at a warmer temperature again. So the warmest temperature would be the young of the year. So this is just to give you guys an understanding of what's going on in these refuges. Of course, none of this is novel. People have been looking at habitat occupancy by salmonids for a long time. That kind of goes back to Huntsman, the 1942 paper, when he was looking at St. Mary's, I think it was 38, 39, and 40. There's folks that have done it in like Cindy Bro, Rick Konjak have done it in our group prior to me coming along. There's folks out in the West Coast, Johnny Armstrong and Dave Schilner, Christian Torgerson, who had done it. Nathan Wilbur did a study there on brook trout and salmon back in 2020. Tern Swang and others have done it. But the paper that kind of piqued the interest of my honor student Alex and I was this Joe Ebersol paper. This is a figure from the paper where you can see these are thermal contours here at 2.5 degrees Celsius. And in this, you can see that the biggest fish is in the coldest area. So that got us thinking, does this hold true for different species, and what's going on with it? So Alex's research question then was, how do salmonids distribute themselves through a thermal refuge? And we had a prediction that larger salmonids will occupy the relatively colder areas of the refuge. Okay, so just for context here, it's Otter Brook. It's a 11 kilometer square drainage in the southwest Miramichi. The flow direction of the brook is this way, the blue arrow. The southwest is this way. This data was collected on August the 13th. Not a nice number for an Irish person to say, on a Friday, so last year. And these yellow dots here, we collected thermal infrared imagery from a drone. The sensor is uncooled, so we needed data points to calibrate the image. So these are simply temperature measurements that we took on the day to calibrate the image. And just for context then, this is a time series of data, actual temperature data over 29 years from this site. And over that 29-year period, so between 1992 and 2021, there was only 9 days that exceeded 30. And luck would have it that we observed the warmest of all of them. The temperature was 31.5 degrees Celsius when we visited it for looking at cameras for a different project. So in terms of data collection, then we have remote sensing data, we had calibration data, and then we couldn't snorkel. It was so shallow, it was about 20 centimeters deep. So we just used polarized lenses. So it's a qualitative study in that regard, a caveat to keep in mind, of course. And then we processed the data, we calibrated the thermal infrared, we populated grids with 1 by 1 meter boxes in a GIS, and then we could start to extract the temperature data and start to look and test if these fish were indeed holding different, were indeed stratifying in terms of age class and temperature. So I want to come back to this idea of a waterscape. So Otter Brook is obviously a cold water refuge, but why is it cold? So that's really the question I want to ask here. So here's the catchment. It's 11 square kilometers. There's got a few wetlands in it, and we can see there's a stream running through it here. This is the main stem of southwest Miramichi, and this is the flow direction of Otter Brook. If you look at the topography, it's relatively high here in the western part of the catchment, and it gets a bit shallow here, where you can see this dominance of wetlands. However, if we look at the depth to bedrock, we can see that it's relatively shallow here. So this DTB is the depth to bedrock. So that's the depth of the superficial geology down to the bedrock, a paper we published in 2021. And we can use those data, to look at what's going on here. So we can see on this eastern part of the catchment, we have a massive gravel deposit. It's actually an outwash plain. And it's about 7.5 meters deep. In some areas, it's about 14 meters deep, so quite deep. And if we think about the geologic setting here, it's glacial outwash plain, as I've stated. It's sand, silts, and gravel, so it's hydraulically conductive. It's deep. It's about 14 meters deep in some instances down in this part of the catchment, and it's on fractured sandstone. So there, if you couple those things together, that's going to hold groundwater. And if we take a look at this profile here, so this dashed line here, and it's also here, we can do a cross section, and the black line here is the topography, and the gray line is the depth at which the bedrock occurs. We can look at that. Here's where the wetland is. So this is this wetland here. Here's where it is. These are the groundwater flow paths that we can conceptualize are coming in here. So this is going from about 70 meters potentially down about 20 meters and discharging into this wetland here. Of course, we have other flow paths that are coming in here, and we may have an even longer one coming from here that will go way deeper than our panel can even show and discharge here again. So this is what's driving the groundwater in Otter Brook. These areas right here, these areas right here are going to drive the groundwater flow path, and they're going to give us that groundwater. So again, it's driven by that waterscape. So, well, why do we care about this? Well, this is work by a mate of mine, Barrett Curlick. Barrett finished his PhD in 2014 in UNB, but he was also working in Otter Brook. So he took some thermal profiles along this branch of the brook here, and you can see that it gets really cold at this point, and it's about 7 degrees Celsius, 7.6 in both June of 2012, very warm year, June 2010, again, a very warm year. This is relatively consistently cold. And he even had groundwater wells down here where he could take measurements at 1.5 meters deep, 2.7, 5.2, and then 8.7. And you can see here that the temperature at this depth, 8.75, is really cold. It goes from about 6 to 7, very little amplitude in it. So if we look at this area here, so this is where Barrett's curve is here. Here's where it gets cold. Here's the curve here. This is what's being fed. So we have this really deep groundwater, superficial geology deposit that is going to feed the groundwater into this wetland. And just for further proof of that, this doesn't freeze in the winter. So this is a paper I published back in 2019. This is from early March, where this is Otter Brook coming out here. It doesn't freeze in the winter. You can see how long the thermal plume is. So the point here is that this is a really resilient waterscape setting. So now let's look at the roller hasn't salmon. So just for context there, we know it's a refuge, but now we know why it's a refuge because we understand the waterscape. And that's important in terms of protecting and conserving the area. Okay, so for Alex's results then, here's the calibration model. So when he calibrated the model, he had an adjusted R squared of 0.97 and a root mean squared of 0.5. That's with a Y-side temperature compared to the thermal infrared. So this is a pretty good representation of what was going on that day. The temperature of the brook is 21 degrees Celsius. Temperature of the main stem is 31.5. So again, go back to that waterscape idea. This is really deep groundwater that has a 10.5 degree buffer between the brook and the main river. It's quite incredible. And then when you look at the distribution of fish here, we can see that young of the year at the very back of this refuge, we have 1+ salmon here, and then we have 2+ salmon, brook trout, and young of the year up in this pocket here. When we look at it across fine gradients, you can look at this map here. Just for context, here's an underwater image. We have 2+ salmon par, there's a brook trout in here, and adult salmon. I want us to look at these profiles here. So first we're going to look at this longitudinal profile, then these cross sections. And before we go and do that, I suppose I'll show you the differences in temperature. So here you can clearly see that the brook trout are tuning into that colder area. Next in line is 2+ par in a relatively warm area than this, but colder than the 1+ par and the young of the year. And then we have this area here, these instances where we have these outliers, but they're not outliers, we know why they're there. It's this group here, and we'll talk about that in a minute. So again, looking at this profile then, this black line is the profile going through here. And we can see that the temperature drops from about 30.5, 31 degrees Celsius down to about 21 degrees Celsius probably. Like it just drops, it floors. And then we have this asymptotic warming as we move downstream due to the thermal mixing. What's interesting here is the distribution of the fish. So we have young of the year in this spot, brook trout, 2+ par, 1+ par, and young of the year. If we look at this cross section here, then we can see it's going from the bank outwards. So we go off the bank, we go from 26 down to 22, and then we have this trough here. So this thermal trough, and where we have that, we have 2+ par plus these 1+ par on the peripheral, so where it's warmer. Then we go down a bit further, and we have, of course, a dominance of 1+ par and the young of the year here, and we go down a bit further again here, and you can see that even though there's a difference of only 0.5 degrees Celsius, we still have this is being used by a thermal refuge by young of the year. Okay, so at the finer scale then, what was really interesting was that we had no fish in here. So if you look at this area here, we've no fish. So even though this is the most thermally stable, and we look at these contour lines here, these are thermal contours at, or isotherms at 0.5 degrees Celsius, we've no fish in the most thermally stable area. What's going on there? Well, if we look at this image here, it's very turbulent water. So we're conceptualizing that there's something going on with bioenergetics here, that it's not just temperature the fish are tuning into, it's temperature plus some turbulence regime that will reduce the energy. Also, we have this young of the year group here. And that's worthwhile noting. This is very shallow. It's about 7 centimeters deep. This is where the young of the year were, nothing else. Okay, and that's where I'm kind of pointing to that. Okay, so just in summary then, Alex has shown that salmonids are stratifying by species and age class, and that importantly, the young of the year will occupy cooler thermal niches when they're available. So we conceptualize that they're hanging out here the young of the year because no other age classes can hang out there. It's so shallow. And then we leave this open question: is this linked to bioenergetics? So that kind of brings me to the next part of the presentation. Okay, so this is a paper we published. When was it? Last year. And this is, again, going back to this idea of thermal regulation, but this time in adult fish. And now we're going to talk about the bioenergetics part of it. So we had a question, a very simple question was, can we quantify changes in habitat use by adult salmon through time as a function of temperature? And of course, we didn't want to touch off them. We didn't want to stress the fish out. We wanted high resolution data, so both spatially and temporally, high resolution data, and we didn't want to work hard. I didn't want to work hard because I'm a lazy bugger. So we thought about this for a while, and we thought, well, frig, we may be able to use drones here. So that's exactly what we did. So just in terms of the framework then, very similar to what Alex did. This time we used remote sensing data, thermal infrared and RGB again, but we had velocity and depth data this time with the RTK, DGPS and the ADCP. We processed the images, we calibrated, calibrated our data. So then we have a thermal infrared image. We have a bathymetric map we built from the passive, from the depth map, from the optical imagery. And then we also built these statistical hydraulic models, and we could start to look at them preferences for different situations or different temperature regimes. Again, so let's pause here for a moment. So this study is going to be based on Black Brook. I want to give a reason why we have this cold water here again. Again, I'm going to keep on hammering this thing because it's important to know why the water is cold. So if we look at Black Brook, then it's an 81 square kilometer drainage, and this is the flow direction of the southwest Miramichi here. The Cairns is here, and this is the flow direction of Black Brook. We have a dominance of upland wetlands, and this is the stream network here. If we look at the topography or the digital elevation model, we have really highly incised valleys in this section here. And this is really important. It's these incised valleys plus the geology that are giving us these Goldilocks refuge zones. If you look at the depth to bedrock, it's a bit deeper across the catchment than what we see in Otterbrook. But again, the geology is going to be similar to what we have in Otterbrook. So the geologic setting is we have a superficial geologies, glacial tills, again, sand, silts, and gravels. They're relatively shallow though, so this looks deep, but in terms of shallowness, like 10 meters is not very deep. Is not very deep bedrock. So New Brunswick is, in general, has very shallow superficial geology. Of course, there's areas where you have outwashes that are 30 or 50 meters deep, but for the most part, it's quite shallow. We have this fractured sandstone, and that's absolutely key here. So that, like it is in Otterbrook, it's the same here. The fractured sandstone that can hold water is super important. The fractured sandstone plus the valley incisions is what gives us the cold water. So if we take a cross section here again, and we look at the black line is topography, the gray line is the depth to bedrock. We look at the Black Brook stream in here, you can see we have an incised valley here dumping groundwater in. We've further flow paths conceptually, and they're coming from all across the catchment. So again, this is going to be a really groundwater dominant brook, and we know that we've data from it. And just for context, this is exactly what we see in the Cairns River here. So again, it's all the same geology here. Where we have these incised valleys, we have groundwater. So that's exactly what we have at Black Brook. So now we know the mechanism of why this area is cold. It's incised valleys into this fractured bedrock that gives us cold water. Again, it's the waterscape. It's very consistent there. It doesn't contract at the same rate that an area that you'd have a granite in. So that's great. Okay, again, so this is a resilient waterscape setting. Let's look at some adults. So here we have a picture of behavioral thermoregulation as about a couple of hundred fish here. It's hard to quantify them. There's hundreds of fish here. And what we can see is that they're all hanging out here. The flow direction is the blue arrow, and they're in the same position during the August behavioral thermoregulation period, and then again during the September period. In August, when the temperatures have dropped back to what I'm calling normal temperature, you see there's no fish here, okay? And when you look at what they're tuning into and look at the thermal infrared imagery, well, they're tuning into the thermal plume clearly. When we look at the depth maps, the velocity maps and the Froude number maps, so they're mapping turbulence regimes, some interesting things start to pop off. So if you can bear with me here, this black line is the thermal plume. And you can see it here a bit more easily perhaps in the velocity map. So we've got a thermal plume. These polygons here are the stools of salmon. So we have them in both. Again, the velocity map may be best to look at that in. And that's it then. So this is excuse me, we'll go back up here. So this is, we have two groups of salmon, which is really interesting, is that if the flow direction is this way, why do we have two groups? This area here would be cooler than down here just because of the thermal mixing downstream. So that's a question we'll come back to. Also, if we look at this area here, this is the deepest section of the pool. There's no fish there. They're hanging out in this shallower area here. So that's something that I'll address as well. So if we look at these preference curves, so I don't like it preference, it's what's available, maybe is a better word to use it, but in literature we call them preference curves. So here you have 0 to 1, where 1 is the most preferred area and 0 is the least preferred area. So the orange circle here in the dashed line is August behavior thermoregulation, what we observed during that time. The blue triangle here is during normal temperatures, and then the green circle is going to be September behavior thermoregulation. So if we start up here first, panel A, and we'll work our way through. So you can see in panel A, if we start with normal temperature first, they don't really care about distance from the plume. They're all about 20 meters away, and that's probably linked to the distribution of other parameters that we'll talk about in a second, their distance from the plume. But once we get into that thermally stressful time, or when they're behavior thermoregulating, you see that they're all within the preferences to be right in that thermal plume, and not surprising. The next thing we'll look at is depth. So even though the depth that's available is up to 2 meters, we see that during the normal temperature regime, they're tuning into about 1.3 meters. So that's interesting. And then for the behavior thermoregulation periods, it's a bit of a wider spread, and we can talk to that maybe a bit more detail in a minute. So there's a wider spread for the depth preference than there is during the normal times. For velocity, there's a clear preference during normal temperatures, but when they're thermally stressed, it varies. It's kind of bimodal. So what may be going on there? The velocity on its own isn't explaining what we're seeing. But when we look at the Froude number, so a Froude number is trying to explain turbulence regimes in the water. You can see that for normal temperatures, there's a pretty wide spread from about 0.06 to about 0.1. But this is the only parameter really where we have a bit of a tightening for the preferences for the behavior thermoregulation. So we'll allude to that back in a minute here. Probably the most interesting thing is this distance from boulders. So when we have normal temperatures, these fish are all within a meter of a boulder. That's really important. So we have got a couple of things going on here. We have the boulders and the turbulence that we got to consider, and of course the temperature. So I've got some illustrations that will hopefully shed some light on that. Just before I do, you can see during the behavior thermoregulation periods, there's no real link between boulders. It's wherever they're located in reference to the thermal plume is probably what's been picked up there. I wouldn't worry about the bimodality of it. Okay, so just for context here, or excuse me, an overview, there's a hydraulic occupancy varies with temperature. That's the main thing. Okay, so here we have an image, a drone image, and we can see some salmon here. So we got salmon here, 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 and yeah, I think that's good. There may be one back there. And we have a boulder here. Flow direction is this way. If we simplify this section here and we just pull out some fish, just for illustrative sake, we have a boulder here and we have these adult salmon. If we look at it in terms of the qualitative hydrodynamics, then I'm just watching my time, and look at the plan view, and then we look at the hydraulic drag. So flow direction is this way. This is what we see. This is what we conceptualize. These salmon are kind of sitting in this sweet spot here where there's less hydraulic drag, but there's also interesting things going on with the flow paths. So we would have upstream recirculating currents that the salmon are kind of surfing on as they face upriver. So flow direction is coming this way, but we have a horseshoe vertex coming up here. It pushes the salmon upstream so they can spend less energy next to that boulder. And Foku fish know this already, but this is just to illustrate. Just a bit of a sidebar here. I don't know how many people are familiar with pelotons and cycling, but typically in cycling, we have these formations where you'd have a sprinter in here, the wind direction may be this way, or it may be this way. And what they're trying to do is protect the sprinter so they don't get nuked with air drag. And just for illustrative sake, then this is a paper by Block et al. And you can see the pressure coefficient or the drag wind speed is lowest in this area here, where the front cyclist, if you go to here, is getting most whacked by the oncoming air. And the sprinter may be back here, where if you look at the percentage of drag compared to the isolated cyclist, it's about 5% lower. Okay, so let's just keep that in mind and look at this picture here. So we can think of the same thing with salmon. We have this thermal peloton, or that's what we're calling it. So you can see that at the very front, you're going to get a bunch of hydraulic drag. So these fish are getting whacked here, and the fish here in the center are going to have the least hydraulic drag. So they're going to be expending the least amount of energy while they're behaviorally thermoregulating. So there's an energetic benefit from where they're located in the peloton. Here as well, so I'm just going to focus on this here. Those boulders that we spoke about, they have an impact about 3.5 times the diameter of the boulder downstream. So you can see here we've got flow direction this way, we've got the recirculating current, and we can see that the boulder is influencing about 3.5 times the diameter downstream. So if we think about these two groups that we have here, so this group is 29.4 meters long, and then we've got a 35 meter space, and we have this group. So remember, this is the plume here. Why are these fish hanging out there if it's warmer? Well, look at this again. So this is showing us that there's a clear preference for turbulence regimes that they're selecting in both instances here. What we conceptualize is that this group here creates a zone of influence where there's an upstream recirculating cell, and these salmon here, so these guys here, are actually using that recirculating cell to face themselves back upstream, so pushing them back upstream, expending less energy. So it's not just temperature we got to consider now, it's the hydraulics. So it's the bioenergetics of the fish. Remember, these fish aren't eating in the river, so they're going to save as much energy as possible to put in towards spawning. So sure, salmon select for cold water, other formations of schooling strategies seem to be linked to a decrease in energetic costs. And we have these bio-derived hydraulic refuges. Okay, so then in summary, hopefully this has come together at the end. I would argue that we have to start considering the multidimensional interconnectedness of ecosystems. So that's a big wordy sentence. Essentially what I'm saying is that to understand thermal refuges and the ecosystem functions, or anything essentially in the landscape, we have to look at the landscape holistically through 4 dimensions of space-time. And this really means that we have to move beyond the topographic catchment, and hopefully I've illustrated that here. And then to protect and conserve these thermal refuges, we have to understand their waterscape setting. We have to understand how they work, what's the mechanism behind their existence. And then clearly within these refuges, Alex has shown that size matters, and we've also, I hope, shown that hydraulics matter. So I would argue that we can collate these waterscapes to biota and then start to develop mechanistic linkages between the two, and that will give us a better understanding of how to protect and conserve these critical habitats. So of course there's a bunch of funders and supporters, so thank you very much. Of course ASCF is there, MBIF, the Government of New Brunswick, Wildlife Trust Fund, Department of Fisheries and Oceans, and then UNB and CRI. So that's it, and if you have any questions, I'll try answer them.
Thanks, Antoine. That was a wonderful presentation. Much appreciated. So now we're at the time of the presentation to open the floor for questions. The way we're going to do that, you will have a button where you can type in your question, and then I will read it out loud so Antoine can answer it. Or you can raise your little hand beside your name, and then I will unmute you, and then you can ask your own question. So I see, I'm not sure if it's really a question, but it's a comment that says, thanks a lot, very interesting. I'm gonna go check here for hands.
That's an easy question.
That's an easy one, yes. We might have to give them a little chance to think about some too, so.
Or I've just bored the arse off everyone.
What? And then there's another one, cool presentation. We need to chat continuum. So we're just getting positive feedback here, which is great. I'm not surprised. Well, let's see here. I think there might be a hand. Well, Antoine, I think you did such a great job, and it was so clear as day. There's no questions, but just to let everybody know, if there is questions that you think of after today, please feel free to email them, and then I can always share them with Antoine, and we can do our best to answer them. So once again, great presentation. This session today was actually recorded, so we're going to be putting that on our YouTube page. It'll be available for everyone, hopefully by the end of the day today. And also before we leave, also to remind everyone that this is a webinar series, so we're going to have one every month. So our next one after today is November 2nd. It's going to be with Shelley Denny. And she's going to be talking about concept of salmon conservation and management from Mi'kmaq perspective and collaborating for effective salmon governance. So once again, big thank you to Antoine and being here, and also for everybody else that participated and joined us to watch. And we hope to see everyone soon. So thank you.
Take care, Charlene. Have a lovely day.
You as well.
Bye-bye.